Hi everyone. My name is Amrinder Singh, and I'm also a PhD candidate in Dr. Hagwardhi's Water Management Lab. And I know I'm the last one, and by this time, probably everybody is thinking about the food that you're going to eat for lunch. So I won't be taking too much time. I'm gonna turn my video off now, uh, just so you can hear me very clearly. My presentation is about autonomous Bermuda grass irrigation using recycled water with soil moisture sensor-based smart controllers. So most of the things that I'm going to discuss, you already heard in Dr. Hagwardhi's and Anish's talk. So few things different that I'm doing compared to Anish's talk is I'm using turf grass as opposed to landscape irrigation, a landscape species as Anish talked about, and I'm using soil moisture sensors along with a smart irrigation controller to make the irrigation decisions, whereas Anish used a weather sensor or ET sensor, you may call. And other thing different about my research is I'm using recycled water for irrigation as opposed to just fresh water. So So yeah, why focus on Southern California? As most of you might be aware that Southern California obviously is like a very population dense region of California, and the population is expected to increase with time. Like it is expected that by 2050, the population of the state is going up to 51 million, and with that, obviously, there's going to be a increase in the water demand. And as you can see on the figure on the right, by 2050, agricultural and urban water demand is expected to increase. While the agricultural water demand may stay almost about the same or might even decrease, the urban water demand is expected to increase. So that's our motivation and why really focus on turf grass. So as you may see here, the figure on the right, you can see turf grass accounts for almost about, here you can see it's 44%, but almost about 50%, especially in summer months when the demand for urban irrigation is higher, of the total water that is dedicated to urban water use. And there was this study that is done in LA that indicated that urban landscapes in general, they contribute about 64 to 84% of urban landscape evapotranspiration. Uh, there was this another study which stated that with turf grass and the amount of area that it occupies over the state makes this about the largest irrigated crop, as it occupies like 2% of the US area. So other than residential areas, turf grass, as we all know, plays a very important role in playgrounds, golf courses, and parks, and which is, you can say, is like a more permanent, or that turf grass permanent goal, or turf grass is expected to stay here longer with these playgrounds and golf courses. So we all know that states with increasing droughts, with diminishing freshwater resources, we need to look for alternative water resources. And so recycled water is a good alternative for that. And there's potential because this 2015 survey by State Water Resource Control Board shows that about 24% of the recycled water is being irrigated, being used for irrigation purposes for landscape, and most of which, as I said, is turf grass. Uh, and so there's potential to increase that even more as state water resource. There are policies that recommend that the use of recycled water is increased. I think it was increased to 2.5 million uh, acre feet per year by 2030. So with that, there needs to be more focus on this. So that was what's the motivation of this research is. But when we irrigate with recycled water, there are some challenges with that. Recycled water is naturally high in salts compared to the freshwater resources. So when you irrigate your crops or with your turf grass or whatever plants with water like that, which is naturally high in salts. Salts tend to accumulate in the top of the surface, as you can see in this figure. So what happens is you are applying water, and pretty much every water has some salt in it. Recycled water happens to have a little more salt than fresh water. So as plants transpire this water, and water also is evaporating from the soil surface, so water is coming up to this top layer. And as the water is evaporating, but all the salt that just is left behind in the top surface here. So if we are not applying, so to help with that, we need to apply even more water so that all the salt is washed down to the deeper layers of the soil. Because if the salt stays there in the top layer, it's going to increase the stress. We call it osmotic stress for the plant roots, and plant will have to exert more energy to take that water out. So since if we're using most of that energy to take the water out, plant growth will be affected, and you can even see like browning, or plant might even die, or we call it drought stress. We won't call it drought stress, but the symptoms are very similar to drought stress. So as you have seen in Dr. Hagordi's presentation, you know how a smart irrigation controller works. So it's smart irrigation controller. You can think of it as a basically timer-based irrigation controller, but it is taking feedback from either a weather sensor, which could look something like this, or soil sensor that you have installed in the soil. So in my research, I will be mostly focusing on the soil moisture sensor, because that's what we used with our soil moisture controller to make all the irrigation decisions. And so why use soil moisture sensor? There have been various studies in humid regions of the state which indicate that, well, these are the states that had high rainfall. So their goal was to use a soil moisture sensor to avoid over application of the water. You can think of it as if there's rainfall, you don't need to turn your sprinklers on. So that's basically soil moisture sensor will do that for you. So all these studies showed that there was about like 50% or even more reduction in applied water compared to fixed irrigation rate. And this is the photo that you see is from one of our plots at Irvine when we were installing these sensors in our plots. So one thing to keep in mind when you install sensor is to just make sure that you have good contact with the soil and the sensor. So you make sure you compact the soil, not too much, but enough that there is good contact. Because if there is no good contact, there might be air spaces between the soil moisture sensor and the soil, which could result in inaccurate values. So we don't want that. So you make sure it's in a representative area of your lawn or your region or irrigation zone, whatever you want to call it. So another concept which just going over again that you all went or you already probably saw in Dr. Hagordi's slide. So there are a few terms that I'm going to throw at you again. So saturation, which is basically is the time when, let's say there was a heavy rainfall or a major irrigation event, all the soil pores are filled with water. So that's what we call saturation. And field capacity is when all the larger pores of the soils are drained and the water is left in the smaller pores. We call it field capacity, or the upper limit. We don't usually want more water in the soil than the field capacity, because then it will leads to runoff. And then there's permanent wilting point. This is the point where the soil moisture is so low that the plant dies. But there's this another term that's called maximum allowable depletion, or MAD. This is the key concept basically. So it's considered the max the amount of water that you want to apply. So the plant is getting enough moisture and it's not dying basically. So if we apply low moisture, uh, low amount of water than mad, that the plant that's not enough for the plant basically, and it will die.
And in there, you may want to speed up a little bit, so make sure that you get to your results of your work.
Oh, for sure, for sure. And so yeah, this is basically the principle behind it, and that's what we used. The figure on the right, I won't go too much into that, but what it is showing you is the blue line on the top is our upper limit, which is field capacity. The lower limit is MAD value, and we played with different numbers of MAD, and I will go over that in the coming slide. What you see is the program, and these zigzag lines is the actual soil moisture in the soil profile, and these blue bars are when controller actually irrigated. This is runtime in minutes. So you would say whenever this soil moisture was close to the lower threshold, that's when the controller started irrigation. So that just means that the controller was working correctly. And just quickly want to go over with what was the layout of our plots. So the figure, that the green figure you see, this is how our plots look like. We have 48 plots with Bermuda grass at South Coast Research and Extension Center, all being irrigated by recycled water. And this table, I'm not going to go into too much detail, but we experimented with two watering day treatments. We were irrigating some of these plots for 3 days per week, and others we were irrigating 7 days per week, basically giving full control to the controller. So that means the controller was making the decision when to irrigate, when to not irrigate. And in all situations, it was only irrigating when the soil moisture drops below these lower limit of the treatments that we had implemented. And in one of this block, we had 4 blocks, as you can see here. We had installed a climate TDT soil moisture sensors, and these are the sensors that controller is taking data from to implement all these treatments. And the other 3 are basically just the replications of that. Replication is very important whenever we do a science work or any experiment. And just quickly, you have seen these pictures in Anish's slide, and I just want to go over real quick. This is the soil moisture controller that is basically connected to all the soil moisture sensors and valves, and is making all the irrigation decisions. We have already programmed it. And on top of that, we are taking NDVI and air temperature humidity readings every week using these handheld instruments. NDVI is basically, as Manish mentioned, tells you how green the plant is. Basically, the greener the plant, the healthier the plant. So it tells you it's the measure of how healthy the plant is in a way.
Ninder, can you go to the previous slide very quickly? I want to point out something. So basically, what we are trying to do here, the objective is to find the optimum lower limit and upper limit thresholds. And our goal is to conserve water, of course. With the lower limit, you can see that we go sometimes as low as 55% field capacity. So we're getting closer and closer to that permanent wilting point. And with the upper limit, what we try to achieve is that if we go beyond field capacity, we know that some of that water would go down deep, would be deep percolation. But since we are applying recycled water, we want to add some extra water to not only fulfill the crop water requirement, in this case turf grass, but also wash the salt down, as Amninder mentioned. So our goal here is that to really go towards that autonomous irrigation, to conserve water and then manage salt, to see if the controller can do that by itself with high efficiency. Okay, Amninder, you can continue.
Thanks, Dr. Worthy. Yep, that was a great point. And another, I will just add to that, just why we are measuring this NDVI and air temperature, because our goal is to save water, but also to see can we save water while maintaining an optimum health of the turf grass. So that's why we're taking this NDVI measurements in a way to quantify the greenness. On top of that, we have two plots where we have a setup like this installed. These are the soil moisture sensors. This is a thermal sensor, and this is spectral sensor, which is also uh, uh, taking readings of NDVI basically continuously. Every 30 minutes, it's recording data to this data logger that you can see. So it's all to answer the same questions, but just different instruments. Instead of weekly, it's taking readings every minute basically, and averaging per half an hour. And on top of that, just as Anish has mentioned in his slides, we're using drone data to collect the same type of data as I mentioned in the previous slide to answer the same questions. We have started doing the drone data just this year, and I'll show some of the results from the weekly data collection from last year in coming slides. And the figure on your right is just the NDVI, basically how green or the plants were. As you can see, the more the green the turf grass is, that means those were the turf grass was irrigated with high amounts of water. In addition to that, we are also doing soil sampling at the start and at the end of the study period, which was May and October last year. And we are only focusing on summer months mostly because, of course, that's when the demand is high. And on top of that, it's a warm season turf grass, and it goes dormant in the winter months. And so why this instrument you see on the left is, it's called Saturo. It's basically measures soil infiltration. Why do we need to measure that? Again, is to see if we are applying different amounts of water, is that resulting in accumulation of salt on the top layer? And does that accumulation hindering the infiltration of water into the soil? So to answer those questions, we are collecting this data. And just quickly, I'm going to go through my preliminary results. So figure on your left is the salinity of the irrigation water. We have a sensors installed in the common inlet at our study site, which is continuously measuring the salinity of the irrigation water. And you can see the salinity varied from almost 1 to 1.4 decisiemens per meter throughout the study period. And this is last year. The figure on top is the soil salinity at different depths of soil, 15, 30, 45, and 60 centimeter depth in the soil. As you can see, at the start of the study period last year, it was well-leached soil, what we would like to call it. But by the end of it, end of the study period, salt accumulation on the surface was more. So it'd be interesting to see how the results are this year. And this is just NDVI data. One thing I would like to point out here is on the left is the 3-day treatment, when we were irrigating 3 days a week, and 7 days is when we basically gave controller full control, or you can call it on-demand irrigation. So it was irrigating whenever it thought that, okay, the soil moisture in the soil is below the threshold that we programmed, and if it's below, it will start the irrigation. And let's say for now, we will say the 0.6 is like the optimum number. Below that, the greenness of the turf, it decreases, diminishes. It starts to turn brown, or it basically doesn't look good, and nobody wants that. So if we were irrigating 7 days a week, the turf grass was able to sustain that greenness for longer period of time compared to 3 days a week. And I won't go a lot into the different treatments, but the recommended usually is the 75%. But what we saw is, even if you reduce that recommended to 65%, we still can see optimum turf grass health while saving some water. And this is the same figure as the previous one. Again, not going into much detail, but in science, we like to really see if this difference in treatments was significant or not. So the difference here between the higher deficit, or you want to call it high, this is the higher deficit because we are applying less water, was significant from the less deficit treatments, or when we were applying more water. So that's just our take-home message, that there's a potential that we can save water while maintaining optimum turf grass health if we reduce the recommended threshold levels a little bit. So that's basically all, and I would like to thank my funding and of course our team, the PI, Dr. Haworthy, and thank you all for coming here and giving me this opportunity to present my research. So